Okay, should be working, I think. Let me just see. It should show that I'm live here, right? My channel, okay. Yep, I'm live. Alright. And it's pretty low latency. Okay. And it's pretty low latency. Okay, let me get a past paper working. Okay, microphone works, that's good to know. Remute subscribe. Thank you. If you go through my channel, you can actually find loads of chapters for the grade 12 physics we had this year. Mechanics, mostly. Alright, I'll have the YouTube video. Okay, so I'll have the live up to my left, so I can see whatever you guys ask when it comes to questions. Um, okay, muted. Alright. So yeah, chat shows up. Okay, let's start with the past paper, I guess. 2020. Okay, I guess let's start with 2022. This is biology. Oh my god, I'm so dumb. Okay. A levels 9702, 22 June. Why do they not have, wait. Oh god, they don't have the syllabus update because I want to show you what's new in the syllabus. 9702. Right, so the new ones that you're gonna see here, we have, so, okay, so 12 we have 13, okay, so 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, and 22, and 23. Okay, so they're all like, everything up until 25 we've had before. Um, it's just that electric fields were moved from AS to A level, and they're removed anything to do with frequency and communication. And then we also have incapacitance, we have RC circuits, so discharging capacitors and all that. So I just want to see if they mention that here. Alright, they didn't. Whatever. I'm pretty sure they did. I just can't find it. So I'm just going to start out with the 2022 past paper because those are the most recent. That's biology. Oh my goodness. Okay. This is physics. Yes. Okay. June. So question paper. We're going to do 42, obviously. Mark scheme 42. Let me just move this over. Okay, perfect. And then we can do this. So let's start with question one, I guess. Okay. Oh, this is the marking scheme. I need the question sheet. Yeah. All right. So wait. Okay. Right. So define gravitational potential at a point. So this is just a definition you're gonna have to know. It is work done per unit mass um, while moving that mass from infinity to a point. So let me just write it down for you. Work done per unit mass where the work is moving the mass from infinity to that point. Because here they're asking about a point. So gravitational potential at a point is work done per unit mass where the work is moving the mass, where the work, no, rather wait, the work is done to move the mass from infinity, where the work is done to move the mass from infinity to that point. Yeah, this is a valid definition. I literally started that one a couple minutes ago. Is there a document for these types of questions? I'm really bad at those. Yeah, actually. Okay, so just take a picture of this or screenshot it real quick so I can move on and show you the document. I'm pretty sure there is. Just let me know in the chat when you screenshot it. You did? Alright, perfect. Yeah, I believe on the website Physics and Math Tutor, which by the way is not just for physics and math, it's for other subjects like bio. You have it here open. Uh, Physics. All right, so physics. I think you have to go to revision. I also want to check papers because there's something I need to see that I also need to show you. So yeah. Okay, never mind. These are just things we're familiar with. Okay, so you're gonna have to go to this and then leave, please. Okay, and then A level. You go to physics and then revision, right? Then you're gonna scroll down to CIE, or no, CAIE, right? Because those are the ones we're doing. And then, okay, so for the topic gravitational fields, because that's the first question. You can see here definitions, flashcards, and like they have detailed notes that you can have a look at. So let me see if they have a definition for gravitational field. These are notes, they probably have it here in definitions. Gravitational field. Okay, looks like they don't have it for this specific definition, but flashcards, they might have it in the flashcards. Right, so you will for the most part find the definitions here. I just didn't happen to find the definition for this specific question here. I think they didn't put it up because it's like a new syllabus, so that's why. Yeah, but like you'll find the important things here, like the definitions and all that. So yeah, here they're asking for gravitation of potential at a point. So gravitational potential at a point. Oh, here it is. Sorry. The amount of work done in moving a unit mass from an infinite distance to that point. Okay, I'm so blind. It's literally right there. So yeah, my bad. I just talked out of my ass and it was literally right in front of me. So yeah, they're asking about gravitational potential in this case. We go have a look here. Gravitational potential here, so it's defined at a point. So the amount of work done in moving a unit mass from an infinite distance to that point. And you're gonna find definitions like these for AS, for A2, for physics, bio, math, chemistry, whatever you're doing. Oh, actually, aren't you doing like all four or something? المهم. Yeah, this is just really helpful. So just type in the chat like you're good with this so we can continue moving on to the questions, right? Like you know where to find these resources. In fact, let me just send you it actually. So this is for all the chapters. You can press on whichever one you want and have a look at the definitions, physics A level, and send. Alright, perfect. Then that's so cool. Yeah, I know, it's really helpful. Alright, so I'll take that as a yes. We're ready to move on. So I'll just close all these. Actually, no, we'll keep them open. We might need them. Just not. Yeah, okay, we'll have it here. So, alright, let's go. Now, define gravitational potential at a point. We just did that here. Now, starting from the equation for the gravitational potential due to a point mass, show that the gravitational potential energy, so EP, of a point mass m at a distance r from another point mass big M is given by this formula. So you have to derive this formula, right? And G we know is the gravitational constant, 6.67 times 10 power negative 11. So you're welcome, of course. So let's just take a screenshot of this. Okay, so for this one, we know that so did they give us any specific variables you have to go with here? Right, so here they just want us to define the potential energy of a mass. Okay, so we know the potential energy is equal to negative, well, negative G big M over R. Now, the potential energy of a mass, so here, the EP, is just going to be phi M. No, oh my god, wait. So, so, so wait. How can I make this simple for you? Yeah, okay, so ignore all the phi stuff. Wait. So we know that gravitational potential is this, right? So this is the formula. We know it from school. And then the gravitational potential of a mass is going to be EP equals to phi m. Wait, I'm having a look at the marking scheme and the answer is fucked. I've done this question before. Let me go through my notes actually. Yeah. Right, and EP is equal to phi m. Therefore, we can just say um, EP is equal to
negative g m over r times small m. I hope you got that. Their definition, it's a bit confusing. Did you get that?
No, I got it. Very good. So, um, let me tell you one thing about like physics A level in general. Whenever they start off with like a definition and it involves a formula, they're 100% gonna ask you to apply that formula. So here, gravitational potential at a point, then derive that formula, then solve using that formula. So let's have a look at the question here. Here they're asking, so here, figure 1.1 shows the path of a comet of mass 2.2 times 10 power 14. So the comet's over here, as it passes around a star of mass 1.99 times 10 power 30. So that's the star over there. At point X, so this is point X, the comet is that much away from the center of the star and is moving at this speed. At point Y, so when it's like hugging the sun, or the star rather, the comet passes its point of closest approach to the star. At this point, the comet is a distance 6.38 times 10 power 10 from the center of the star. Both the comet and the star can be considered as point masses. Okay, so calculate the magnitude of the change in gravitational potential energy of the comet as it moves from position X to position Y. So here. So we need to calculate the magnitude of the change in the gravitational potential energy. So we know gravitational potential energy is just between two masses is U or EP, whatever. I'm just going to refer to it as U. Actually, no, they refer to it as EP in the marking scheme, so I just refer to it like that. EP equals to negative G big M small m over R. Now, in this case, R is changing, right? The distance is changing. First it was here, now it's there, and all that. So it's going to be um, R final minus R initial, right? Yeah, it's going to be R final minus R initial. So we can just simplify this formula and make it look like this. So EP equals negative G big M small m over, no, negative G big M small m times 1 over, because we just factored out this, right? And sorry, we factored out all of this. So 1 over R final minus R initial. So what's our final, just one here, the distance? So 6.38 times 10 power 10 minus, what's the initial distance? So 8.44 times 10 power 11. So here, so negative 6.67 times 10 power negative 11 times big M, so the mass of the star, passes around the star of mass 1.99 times 10 power 30, so 1.99 times 10 power 30. Times small m, which is, oh, okay, so here 2.2 times 10 power 14, so 2.20 times 10 power 14 times, and then you open bracket, calculate, fraction, calculate a fraction, 6.38 times 10 power 10, right? Yeah, times 10 power 10 minus 8.44 times 10 power 11. So we did something wrong. Calculation error. Did I put this in the calculator correctly?
Oh, wait, I think. Yeah, I just put it in the calculator wrong, I believe. So 1 over 6.38 times 10 power 10 minus, yeah, it's supposed to look like this, I believe. Then we'll get the right answer. 8.44 times 10 power 11. Yeah, so this is the correct answer. So make sure you put it like this in the calculator. Don't make the mistake I did, okay? Are you good so far? Do you understand how we got to this point? I'm waiting on a reply. Are you there? Can you hear me? Oh shit. Okay, I'm just gonna assume you got. Oh, okay, perfect. Yes. All right. So, okay. So now we got. What was our answer? We got negative 4.23 times 10 power 23. So negative 4.23 times 10 power 23. Was it? Times 10 power 23. Yeah. And keep in mind I did do a little mistake here. Not a mistake, but um. So this negative is going to help us answer the question afterwards, but you shouldn't put it in your final answer. And the negative one here, in the negative g, you should leave it out, but it's going to help us answer the next question. So for now, we're just going to put down 4.23 as 10, times 10 power 23 into the paper. When you're solving, this is what you put down. And then the question afterwards is going to be state with a reason whether the change in the gravitational potential energy is an increase or a decrease. Hello, when we solved, we had a negative answer, so we know it's a decrease. Now we need to state why it's a decrease. So this is a one more question. You're just going to say, since gravitational force is an attractive force, then the work needed is decreased, right? Because um, obviously it's a force that acts by attracting things closer to it. So when you're attracting something that is much, much farther away, you're going to need to apply a lot more work. Whereas the object here, so at point X, it's applying much more work than it is applying at point Y, and it moved from point X to point Y. Therefore, you're going to say force is attractive, so a gravitational force is attractive, so the change in gravitational potential energy is a decrease, or you can say gravitational force does work, so decrease. Now, next question. Use your answer in part B to determine the speed in kilometers per second of the comet at point Y. So, um, actually, I'm gonna have it on paint. It's much easier like that. So. Right. So our answer for part B, I, was 4.23 times 10 power 23, correct? Yeah. Okay. So, now they want the change in gravity. Okay, so now they want the speed of the comet at point Y. So, speed, and we have work done. Work done is in the unit joules. So, what do we know about that? What can we get? How can we get speed from joules? So, um, So from work or from energy, right? Here, energy. How can we get speed from energy? We know the energy for kinetic form, if the formula for kinetic energy. So EK is equal to half m v squared, right? Now, this is potential energy, okay? But by the law of conservation of energy, we can say that EP equals to EK. So we can now say, can I increase this? Yeah, okay. So now we can say EP equals to EK. Therefore half m v squared, and here they want it from point y. So we're going to have to take the initial speed and the final speed, because y is where it where it ended, x is where it started. So we're going to rewrite v squared as v final squared minus v initial squared, and we have v initial, right? Now make sure you write it like this and you don't write v final minus v initial all squared, because this will give you a wrong calculation, okay? Please be careful. Because if you write it as all squared, then you're going to be applying the rule to, was it a squared minus 2ab plus b squared, and this is wrong in this case, so you're going to have to individually square them on the calculator. So, yeah, so half mv final squared minus v initial squared, just get rid of this. Equals to, and then 4.23 times 10 power 23. So 4.23 times 10 power 23. So, now we're going to be solving for v initial. So, we're going to be solving for v final, my bad. I'll be solving for this. We have v initial, we have mass, and obviously we have EP. I just substituted it in. So, let's see here. Half times m. Now in this case, m is going to be the mass of the comet, or the thing that's orbiting the star, because we're talking about the speed of the star, as you said in the question. No, of the comet, sorry, of the comet at point y. So we're gonna have to put in the mass of the comet. So m is 2.2 times 10 power 14, half m. Okay, and then v squared we don't know. V final squared we don't know, minus V initial squared we know. So V initial is 31.4 kilometers per second. They want the answer in kilometers per second, but you're going to have to convert it to meters per second first before you can convert your final answer to kilometers per second. Okay. So here it's 31, okay, so 34.1. So wait. Yeah, 34.1 times 10 power 3, all squared, and then close up this bracket. Equals to 4.23 times 10 power 23. Solve for x, so solve for v final, or just v at point y, and we got in meters per second v final, or v at point y, equals to 7. Okay, so this is in meters per second, right? 70769. Now they want the answer in kilometers per second, so we're just going to divide by 1000. So 1, 2, 3, so 70. Now they also want it in 3 significant figures, because if you have a look at the question, it's also 3 significant figures. So 70.8 kilometers per second, and that's correct. So I'm going to move on to the next part. So a second comet point, I can't talk, passes point X with the same speed as the comet in B and traveling in the same direction. The comet is gradually losing mass. The mass of this comet when it passes point X is the same as the comet in point B. State with a reason how the path of the second comet compares with the path shown in figure 1.1. So, um, شو اسمه the path is all about the potential energy. So the path it's moving is obviously related to the potential energy and the kinetic energy, right? Now, if the so let's have a look at the formula for potential energy, right? Potential energy equals to negative G big M over or GM over R, whatever, right? And then the formula for kinetic energy is EK is equal to half mv squared. Now they said the second comet passes point X, so it's passing by here, with the same speed as a comet in B and traveling in the same direction. This comet is gradually losing mass. The mass of this comet when it passes point X is the same as in the comet in point B. So if it's the same mass when it passes this point, then it's essentially the same as the original comet. So we can just say the path is not changed. You understand? Just type in chat quickly if you understand. Because from where it initially started passing by the comet at the original comet at point X, it had the same mass. So therefore it had the same EP and EK, so it's going to have the same path. Yes? Oh wow, capital letters. Okay, I guess I'm really helping. I'm glad to know. So, that's it. All right, next question. Hello. So, Coulomb's law. Coulomb, okay, let's see. Coulomb's law, you should know this, but if you don't, I'm going to do you a favor here. We're going to go to electric fields. Can you open? Thank you. And go to definitions. And then, oh, that's fucking tiny. Okay, wait. Hello, Rafig. Okay, wait. No, zoom in, please. I need to read you. Okay, so electric potential. Is that what they wanted? No, they wanted Coulomb's law. So Coulomb's law is that's a long ass fucking definition. Don't even look at that. What is Coulomb's law in general? Coulomb's law is, well, we all know Coulomb's law. So yeah, when I write it down, you know it's electric force. I'm gonna refer to this as F and then electric. That's not an F, Ali. Oh my goodness, you're fucking retarded. Okay, so F E equals to K Q1 Q2 over R squared. You're familiar with this. You've seen this hundreds of times. So now we can say Coulomb's Coulomb's law states that the force is directly proportional to the product of the two charges, right? Because what is this, right? This is Q1 times Q2. So force electric is proportional to their product, and it is inversely proportional because we say they're proportional because here this is in the numerator and here this is in the numerator also. And then we say that force electric is inversely proportional to the square of the distance between those charges. R is essentially the distance between these two. Square of the distance, why are we saying that? Because it is R squared, right? So Coulomb's law states that the force is directly, and you need to state that, proportional to the product of the charges and inversely proportional to the square of the distance between them. In the marking scheme, they said electric force is directly proportional to the product of the charges, and force between charges, I don't think you need to put that. So the force, oh yeah, actually, this force is acting between those 2-point charges is inversely proportional to the square of their separation. Separation, distance, the same thing. Let's have a look at the definition here. The size of the force that acts between 2-point charges is proportional to the product of their charges and inversely proportional to the square of their separation. It is attractive for opposite charges and repulsive for like charges. I mean, we know plus and minus, they attract. Plus and plus, they are plus and minus attract, and then plus minus, and then plus plus or minus minus, they repel. So that's the definition. Where's the past paper? Here. Okay. So positronium is a system in which an electron and a positron orbit with the same period around their common center of mass as shown in this figure. So the radius r of the orbit of both particles is that. So explain how the electric force between the electron and the positron causes the path of the movement of the moving particles to be circular. So whenever you have, is this, oh, it's a 2 mark question. Okay. So whenever you have, in general, this is a law for UCM, whenever the force is directly proportional, the force is perpendicular to the path of the velocity, you're going to have circular motion. Okay, this is a law, you're going to have to understand it. There's a distinct chapter about this, but there's no distinct questions for this. They ask it throughout the entire exam. So if you look here, you see motion in a circle. There is no actual like question for motion in a circle. You just see it all over the place. So yeah, this is really going to have to understand. So here it's a 2 mark question, I would say. And let me just draw this for you actually. So we have the circle. Where is the circle? That's not a circle. This is a circle. Yeah, okay. And then we have like the 2 little things here, the balls. Okay. And then we have their path. So at this instant, right, it is heading towards this direction. So it is heading in this direction. And let me just draw something here. All right. So if we want to know that these are UCM, this is the direction of the velocity, right? And the force is, if it's actually moving in a circle, then the force has to be perpendicular to it. And to the center of the circle, so the force is acting in this direction, right? That's not F. Why do I keep drawing letter E instead of F? Okay, and same thing goes here. Whenever there's UCM, the force is perpendicular to the velocity, the direction vector of the velocity. So force acts in this direction. Therefore, you're going to have UCM. So, their answer. Electric force is perpendicular to the velocity of the particles. And here, the path is it's always this shape. You know, you could have some instances where the path is spiral because the force is not constant. But here we can see in the question that the path is constant. It's not a spiral, it's just a constant circle. Then we can say, and the force has a constant magnitude, because if it had a changing magnitude, say for example like this, here it was like 20 newtons, then it became like 10, then 5, then 2.5. So yeah, you're going to have a spiral, but in this case, the circle is constant, so you're going to have a, a uniform circle, so uniform circular motion. So the answer is electric force is perpendicular to the velocity of the particles, and force has a constant magnitude. Now, next part. Show that the magnitude of electric force between the electron and the positron is that. So I love these questions where they say show, because if you get a wrong answer, you know, right? So what is the formula for electric force? Here they asked us for a definition, and here we're going to apply it, which relates to what I said earlier. Remember, I said they're always going to ask you, if they ask you for a definition, they're probably going to ask you to apply that definition also in the form of the algebraic calculation with the formula. So F equals K, which is a constant. We're going to have to write K as
because okay, so k is equal to 8.99 times 10 power 9. We're always going to have to refer to it in our solvings as 1 over 4 pi epsilon naught. So this is permittivity of free space, so 8.85 times 10 power negative 12. They give it to you in the beginning of the exam, so don't worry, you'll find it here. Permittivity of free space, 8.85 times 10 power negative 12. So 1 over 4 pi epsilon is 8.99 times 10 power 9. Right, okay, did they give us any other here? So we're also going to need, so F equals K times Q over R. And we have the distance R, so no, R squared. Don't forget R squared, okay? So um I think the charge is just going to be, yeah. So the charge of an electron, so just, or the elementary charge in general, is 1.6 times 10 power negative 19. Here it is a positron and an electron. And what is a positron? You may ask, positron meaning. So it's an electron, but positively charged, right? So it's just an electron and an electron. So your formula, your thing is going to look like this, right? So F equals to K, which you're going to have to substitute with all this, or 8.99 when you show you're solving, um, times 1.6 times 10 power negative 19, all squared, since they both have the same charge. So something, so q times q, if they're the same, then q times q is just q squared, and the q is 1.6 times 10 power negative 19. So 1.6 times 10 power negative 19 all squared over the distance they gave us, which is 1.59 times 10 power negative 10. Make sure it's always in meters. Okay, whatever, I'm just gonna write it down in the calculator. So 1 over 4 pi times 8.85 times 10 power negative 12 times um, the product of their charges, so 1.6 times 10 power negative 19 all squared over the distance, which was 1.59 times 10 power negative 10, so 1.59 times 10 power negative 10 all squared. And you're gonna get, we didn't get that. We didn't get this, so we did something wrong. Let's see what it did wrong. Pretty sure it's also something calculation related. Hmm, that's interesting. What did I do wrong? I'm looking at the answer again. What if I just try putting 8.99 times 10 power 9? Yeah. Let's just try putting that instead. So 8.99 times 10 power 9. Still wrong. What the fuck? Hello? Did I put something wrong in the calculator? Am I blind? No, wait. Huh? Diameter. No, what do you mean? Oh my. Yeah, okay. I'm dumb. My bad. My bad. Yeah. Alright, so yeah. So this is the answer. We just got it. We proved it. 2.28 times 10 power negative 9. 2.275, so 2.28 times 10 power 9. Okay. Yeah, thank you. Oh my god, I would have never noticed that. Thank you. Oh my god. Okay. Hello. Hello. Starting off dumb. Let's go. Use the information in, okay, to calculate the period of the circular orbit of the two particles. Okay. So so calculate the period. Okay. We what did we get? Oh, they give us the answer here. So 2.28 times 10 power negative 9. So how could we do this? Okay. So we know that, so okay, since these are moving in UCM, we can also apply the formula F equals mv squared over r, right? So we can, and F is equal to k q over r squared. So we can just equate these two together, right? Yeah. So mv squared over r equals to k q over r squared. So we can cancel out this r and then cancel out the power. So it's going to be mv squared equals to kqq over r. And we're looking for the period here. We know we can get the period from v because v is equal to 2 pi r in this case. 2 pi r over t, because again, it's moving in circular motion. So, m, what's the mass in this case? Here it's the mass of an electron, and it's also like and the positron is also an electron. So mass is the mass of the electron, so 9.11 times 10 power negative 31. It's given in the, the tiny data sheet they give you in the beginning of the exam. So then 9.11 times 10. Okay, I'm just gonna slam it into the calculator. We know this, we know this, we know this, and we know this. So okay, so 9.11 times 10 power negative 31 times v squared we don't know. V we don't know in general. I'm just gonna put v squared. Okay, so equals to k, which is 8.99 times 10 power 9 times q. So what's q? Right. So 1.6 times 10 power negative 19 all squared over, now the diameter, I'm not going to make the same mistake, is 2 times 1.59 times 10 power negative 10. And then we just solve for v squared, so I got this value for v, because it instantly gives us v, not v squared. So let me just double check that one more time. So m times v squared equals to k times q over r. Okay, yeah, so our answer is this. So v is equal to, let's just take it to three significant figures. 89891,000. Now v is equal to 2 pi r over t. So now we're solving for t. Now we're solving for the period, okay? So 891,000 equals to 2 times pi times r. What's the r in this case? The radius, not the diameter. So 1.59 times 10 power negative 10 over t. So for x, and we got a t of, okay, let's just use the exact value. No, oh my god. No, hey, come back. Oh, no, wait. 8, 9. Let's use the exact value. 891. Yeah, actually, I was wrong for not using the exact value. You only round in your final answer. So 891,306.513. So this is v equals to 2 times pi times r over t, which is what we're looking for. And oh my god, that was scary. Notification.
Huh? My answer is so close to theirs. I think it's within margin of error, but still, I don't know. Okay, let's not make it a two-part solution. Let's make it a one-part solution. So wait, so what is this? So we got a really similar answer to them, but not quite similar. So what they did is they solved right away for t. They didn't make it a two-step solution. So that's what I'm gonna do. So again, mv squared over r equals to k q over r squared. Now I just simplify it real quick. So cancel out this and cancel out that. Now, what's v squared? I know v squared is equal to v is equal to 2 pi over t. So v squared is 4 pi squared r squared over t squared. So m times 4 pi squared r squared over t squared equals to this. And then they solve for t. So I'm just going to do that right away. So 8.99 times 10 power 9 times 1.6 times 10 power negative 19 all squared over what's r? R is 1.59. No, oh my, I made the same mistake again. R is not the radius. Holy shit. R is the separation between them. Oh my god. So this R is actually different than this R. This is the radius because this is the radius of the circular motion. This R, so so that means we can't even cancel them out. That's what I was doing wrong. Okay. Oh, that's so dumb. Guys, don't be as dumb as me, please. Right, so this R is different than this R. Okay? Fuck's sake. So um M over R times V squared, so 4 pi squared R squared T squared equals to K Q over R squared. I'm gonna I'm gonna use a capital R for this so I don't get mixed up and mess up again. So let's try that again. Hopefully I get the right answer. I should get the right answer like this. So 8.31 times 10 power negative no. What? 9.11. So 9.11 times 10 power negative 31 over the radius of the rotation, so 1.59 times 10 power negative 10 times 4 times pi squared times r squared over t squared. Uh, this is also the radius of the rotation, so this is fine. We can just say 1.59 times 10 power negative 10 all squared over t squared, which is what we're looking for, or just t only rather, and then k times q, 1.6 times 10 power negative 19 all squared over r, the separation, so 2 times 1.59 times 10 power negative 10. Now we solve for x, and I am going to kill myself. Why is this wrong? Like, what am I doing that's wrong? I didn't square them. No, I did square them. Okay, I'm just gonna go off with their answer in the marking scheme. So they said F equals mv squared over r, and v is equal to 2 pi r over t. Oh yeah, that's actually so much easier. I'm dumb. We already have the value of f. We already have the value of f, which is given to us 2.28, no, wait, 2.28 times 10 power negative 9. And we can substitute this into this to find t. So we're going to get a much accurate answer, because the last time what I was doing is I wasn't getting like a accurate answer to what they wanted. So 2.28 times, so I'm gonna put it to the calculator right away. I hope you're understanding so far. I fucked up like 3 times. I'm really, really sorry. Are you still on track with me though? Okay, you're good. 2.28 times 10 power negative 9 equals to mv squared over r. Okay, so let's just get rid of this. V squared over r. So we can rewrite this as m over r times v squared, where v is equal to 2 pi r over t. So to square that would be 4 pi squared r squared over t squared. So m over r times 4 pi squared r squared over t squared. Did I square pi last time? Okay, I did. 4 pi squared r squared over t squared. Yeah, in that case, I have no clue what I did wrong back then. So 2.28, no, 2.28 times 10 power negative 9 equals to the mass, which is 9.11 times 10 power negative 31 over the radius, so mv squared over the radius of the rotation, so 1.59 times 10 power negative 10 times 4 times pi squared r squared, so this is also the radius of the rotation, so 1.59 times 10 power negative 10 all squared over t squared. Please, for the love of God, be correct. And what did I do wrong this time? What? Shuad! 2.28 times 10 power negative 9. Okay. Uh, yeah. Correct. Okay. So for x, cancel. What? Huh? Calculator, you can't solve it. Okay, let me simplify it, I guess. So m over r is 5.72956. I'm going to take it to nearly the same value so we don't get a calculation error. Times 10 power negative 21. So now we can eliminate this and just replace it with that number. And then let's swap these two. So t squared. So t squared is equal to 5.72956, so 72956 times 10 power negative 21 times, so this is all equal to t squared. Remember, when we get the final answer, we're going to have to radical it. So times 4 times pi squared r squared, so 1.59 times 10 power negative 10 all squared over 2.28 times 10 power negative 9. And then radical this. Finally! Yay! I got the right answer. So don't overcomplicate things. Just don't be like me. Okay, I'm dumb. You're smart. Uh, where's my cursor? Hello. Okay. So just take it easy. Right? Don't. Whatever this is, I have no clue what I did here. I was probably onto something, but I just substituted wrong values. Either way, we got for the value of t, the period, 1.58 times 10 power negative 15. Finally, okay, let's go. Positron is highly unstable. After a very short period of time, it becomes gamma radiation. Describe how gamma radiation is formed from two particles in positron. This is just something you're going to have to understand. So, um, electrons. So so what is an antiparticle? An antiparticle, I believe, is just a particle that is an opposite charge of the particle. It's like it's like so you have particle and then the opposite of it. So the electron's antiparticle is a positron. So when the electron and the positron interact, um, knowing that the positron is the antiparticle of an electron, annihilation happens. So this is called pair annihilation because they're a pair, right? Um, Electron and positron, they're pairs, they're opposites. Therefore, the mass of the electron and the positron is converted into photon energy. Here in the marking scheme, they have, so you're supposed to have 3 points, okay? They're gonna give you 2 points for electron and positron interact, and positron is antiparticle of electron and annihilation occurs, and they're going to give you 1 point for mass of the electron and positron is converted into photon energy. Um, this is something related to photoelectric emission. So, for this one, I would just say electron and positron. So electron and positron interact. Therefore, pair annihilation occurs. And you're gonna have to know how to spell annihilation. No autocorrect in written exam, so annihilation. Yeah, okay. So not pain, oh my god, pair. Pair annihilation occurs. So these two are 2 points, 2 marks, and you're gonna have to, and to get the last mark, you're going to have to say mass of the electron and positron because they have mass, right? The mass of an electron, although it's really small and considered negligible, it has a mass, which is 9.11 times 10 power negative 31. So mass, so I'm just gonna write m of E and of the positron, so and positron is converted, so converted into energy. Obviously, write a full sentence in the exam, don't write whatever this takhbis is, but yeah, that's 3 marks, and that's 3 marks, so I hope you get the A star. Now, state one medical application of the process described. PET scanning. Medical physics, you're going to have to memorize it across the board for physics A level. So, yeah, it sucks because you're going to have to memorize a lot for med, which is foreshadowing med school, but oh well. Define specific latent heat of vaporization. So, you can just write down the formula, or write it out in words. Thermal energy per unit mass, where the energy to change state between liquid and gas at constant temperature. So, um, vaporization, vapor. Think, Lol, I didn't touch that chapter yet. Uh, med physics. Yeah, no, same by the way. Oh shit, I need to. Fuck. That's bad, actually. Uh, Nice, I can't forward it. I was trying to forward you. Ya Allah. I was trying to forward you these. They're pictures from med physics. Oh, I can just do it here. Okay, physics A level. This is basically, I believe, all you need for med physics. So, like, 9 messages can be forwarded. Hello. خلاص, I'll send them from my phone in that case. Let me just delete these now so you don't get any confusion. These for everyone. Okay. Define specific latent heat of vaporization. So no past papers for it. No. I could have sworn I saw. I believe they added to it, but it's not new because I could have sworn I saw a medical imaging question in like a 2016 past paper or something. Okay. Oh, the astronomy. The astronomy. Yeah, no, astronomy is new. No. Astronomy, yeah. No, I didn't see your astronomy message. Yeah, astronomy is new. But I have questions for it, don't worry. So, latent heat of vaporization is just thermal energy per unit mass to change state from liquid to gas at a constant temperature. Okay, because vaporization, think of it as like the vape, where it's like a liquid changes to gas, so liquid to gas. Okay, now next question, we're going to have to apply the definition. Wow, who would have thought? Okay, so Q. Okay, so what are they asking for here? Calculate the thermal energy. Okay, so what is thermal energy? We know Q equals to mL. Hello. Now, what's the mass of liquid? That, okay. And what's the latent heat of vaporization? That. So let's say you just multiply this by this, right? Yeah. Hello. Okay, so just quickly, 0.37 times 2.3 times 10 power 6. 8.5 times 10 power 5. So 8.51 times 10 power 5. Take it to two significant figures here because they gave you two significant figures. So 8.5 times 10 power 5. Yeah, okay, whatever. Next. The mass of 1 mole of water is 18 grams. Assume that water vapor can be considered to behave as an ideal gas. Show that the volume of water produced is 0.64. So we have number of moles, they want volume, we have pressure, and we have, so what do we have? We have pressure, correct. Volume, we need. We have number of moles, yes. Um, and we have a temperature, T, yes. And we have a gas constant, which is 8.31. We have this, so therefore we're going to apply PV equals to nRT. So P in pascals, right? Yeah, P in pascals. Okay, so 1.0 times 10, so 1.0 times 10 power 5 times V equals to 1 mole, right? No, no, not 1 mole. Because here they said the volume of water vapor, right? Uh, and here they told us 1 mole is 18 grams. Here they're not asking for one. Here they're not asking for the volume of 1 mole of water, they're asking for all of the water. So to find number of moles, it's just mass over molar mass. So what's the mass of water? We have 0.37. We're going to have to convert that to grams when finding number of moles. So 370 divided by 18. And we're going to get 370 divided by 18 is 20.5. So let's just cut this out real quick. So 20, no, please, okay. 20.5. So PV equals to nRT, R given to you 8.31. Don't get confused with the chemistry one, which is 0.08206. And T, which is supposed to be in Kelvin, so 100 degrees Celsius to Kelvin is 373, because 100 plus 273 is 373, so. And solve. So 1 times 10 power 5 times volume equals to N, so 20.5 times 8.31 times 373, so for X. And we got 0.635 or 0.64. Next.
Assume that the initial volume of the liquid in the water is negligible compared to the volume of the water vapor produced. Determine the magnitude of the work done by the water in expanding against the atmosphere when it vaporizes. Okay. So the work is just going to be P delta V. That's the formula for it. So work equals to P delta V, where V is volume, not velocity. Okay. And then P is pressure. So what is delta V? Initially, to 0, right? And then it expanded to 0.64. So 0.64 minus 0 is 0.64. And then P, we have it, so 1.0 times 10 power 5. 0 times 10 power 5 times 0.64 gives you 6.4 times 10 power 10. Times 10 power 4. Shoot, times 10 power 10. Okay. Now use your answers in the previous part and the part before it, so part 1, to explain the increase in internal energy of the water when it vaporizes to 100 degrees Celsius. Explain your reasoning. So first we're gonna have to solve it. So the water does work against the atmosphere because it is working against the pressure applied on it by the atmosphere to become a gas, right? So the work done on the water is negative, or the work done on the atmosphere is positive. Here,
Um, they want the internal energy of the water. So water is doing work. That's not water, that's an M. So water does work on atmosphere. Therefore, the work done on water is negative. Hope you understood that. It's a complicated thing to understand. I won't blame you if you didn't.
so then increase in internal energy is, so what's internal energy? Internal energy is Q plus W, if I'm correct. Let me just double check. So yeah, the formula is, it's Q equals, let me just double check this formula real quick because, well, this isn't really my best chapter, so yeah. Like I'm looking at the marking scheme as we're going for this question, and the marking scheme is not all that clear. So water does work against atmosphere. I got that correct. Okay, nice. Increase in internal energy. So yeah, okay. So the formula for the increase in internal energy is what the fuck? I'm sorry, I can't figure this out. What's so Q equals delta U minus W. We're gonna get back to this because I don't want to waste more time and stop on a question. So just remind me near the end of the video to come back to this question, okay? Alright. Shit, I did solve this past paper before. Let me just look at my solvings actually. Use my brain. No, I didn't solve this one. I solved 2021. Well, at least it'll be easier for us when we do that one. So yeah. Alright, I'm sorry I couldn't answer this one, but I'll get back to it near the end of the video, I promise. So I'll just type in chat Q2 last part. Alright, lovely. So state what is meant by resonance. Resonance is when the frequency, so wait, let me just double check it. Yeah. When the driving so no. Well, first of all, what is this question either way? This is relating to simple harmonic motion, right? So the definition of resonance, you can also find it in the definitions for the from this website. So you're going to be looking at oscillations, right? Or simple harmonic motion. So the definition is give me a second, I'm gonna have to grab my charger. Alright, have my charger, sorry for the delay. So, resonance is when the oscillations of an object are at maximum amplitude due to the driving force, due to the driving frequency being equal to the natural frequency. So, um,
how do I explain this for you? So, say for example, you have a stand, right? And then a pendulum. Okay. If you were to just hold it, so the pendulum would be over here, and then you let it go, it's gonna oscillate on its own, right? So let's say this oscillation has a frequency of 15 hertz. So now let's say I take this pendulum and I smack it, okay? So I literally I move it with my hand. And this driving frequency or this driving force gives a frequency that's also equal to the natural frequency, which is 15 hertz. In this case, you achieve resonance. So resonance is the oscillation of an object at maximum amplitude when the driving frequency is equal to the natural frequency of the object. Now, next question. Calculate the period of the oscillations. Period is let me just cut this. So period omega equals 2 pi over t. So here we have omega from the variation formula that they gave us, which is 5 pi, right? So we know omega is equal to 5 pi. So 5, that's not how you write a 5, already. 5, that's not how you write pi, holy shit. 5 pi equals to 2 pi over t, and then replace. 2 pi over 5 pi. Pi cancels 2 over 5, 0.4 seconds. Alright, next. On figure 4.2, label both the axes with correct scales. So, here. This is the light pendulum, okay? Now, in the So let's actually read the given because I just skipped straight to the question. So figure 4.1 shows a heavy and a light pendulum, both suspended from a the same piece of string. The string is secured at each end to fixed points. Both pendulums have the same natural frequency. Okay. The heavy pendulum is set oscillating perpendicular to the plane of the diagram. As it oscillates, it causes the light pendulum to oscillate. So it is Right, okay. So figure 4.2 shows the variation with time t of the displacement of the two pendulums for 3 oscillations. Alright, perfect. So the variation, this is of the light pendulum. Okay, so we know that the period is for the light pendulum is equal to 0.4. So this is our light pendulum. So it completes an oscillation every 0.4 seconds. We're going to write down 0.4 here, and then 0.8 here, and then 1.2 here. And then, so this is 0.4, you're also going to have to label the half mark. What is this? Who's texting? Okay, so this is going to be 0.2, 0.4, so 0.2, 0.4, 0.6, 0.8, 1.0, 1.2. And then for the x-axis, so the amplitude, um, it's going to be so 0.25 sine. So I believe this is half our amplitude value. Wait, so David was in the formula sheet actually. I believe they do. Simple. Okay, formulae. So velocity of particle is u cosine omega t. So v equals u cosine omega t. So x would be Yeah, how do we get the amplitude in this case? Yeah, I believe the amplitude is just double the coefficient of sine. Yeah, yeah, it is. Okay. So in this case, the amplitude for the amplitude for the light pendulum is going to be 0.5. So you're going to label this as 0.5, and then you're going to label this as negative 0.5, and then you're also going to you're going to add um, to the 0.5. So this is from the 0 mark. This is how high up is it? Wait, so let's see. This is 1, 2, 3, 4, 5. So 5 boxes up, you put 0.5. 5 boxes down, you put negative 0.5. And then you go another 5 boxes up, put 1.0, and then another 5 boxes down and put negative 1. You're going to need that. No, it's not just 0.25. The amplitude here, I believe it's 0.5. So 0.5, and then 1.0, and then negative 0.5, and then because they said V, what was it, V0 or whatever, no. V equals V0 cosine omega t, right? Yeah, V equals V0 cosine omega t, because V0 cosine omega t. And to get to this here, we know that v is equal to dx over dt. So I'm just going to quickly try to derive this formula for you. I believe this is how you derive it. So dx over dt equals to v0 cosine omega t, and then you move dt to the other side. So I'm just deriving the formula for you real quick here, dt, and then you integrate. Integral of dx is just x, and then um, integral of v0 is going to be uh, yeah, wait. Oh, fuck me, man. I could have saw something before that. Yeah, so xt is equal to a cosine omega t plus, so the amplitude, yeah, you're right, isn't it just 0.25? I guess, yeah, it says just 0.25. Let me double check. Yeah, so it is just 0.25, but they want you to label it every 0.5 for some reason on the graph. I don't know why they want that. They overcomplicate things so much, it's annoying. Wait, let me just double check what I'm looking at here. So this is, no, this is sine. What I'm looking at here is cosine. Yeah, here. Velocity is, displacement. We have displacement, right? Yeah, displacement. So amplitude sine 2, sine 2 pi, and then frequency in time, so that would just be omega, right? Yeah, so the amplitude is just 0.25, but they want you to label it every 0.5. This is annoying. I'm sorry. Yeah, I'm sorry, guys. Again, I couldn't give you a clear answer for this one. So yeah, this is that question done. And now we're this one here. So determine the magnitude of the phase difference between the oscillations of the light and the heavy pendulums. Give a unit with your answer. So phase difference formula is just the formula for phase difference. So phase difference is represented like this. Phi is equal to 2 pi delta t over period. So we're going to look at the graph here, and let me just, I have this graph labeled, so it's okay. Yeah, yeah, so this is correct. They just want you to label it fully. So the amplitude is 0.25. Yeah. Okay, so now we're going to be getting the phase difference. So um phase difference is just going to be the difference between the two strings. So 2 pi and then uh delta t over t. So what do we have here? We have 2 pi, so let's just simplify the formula. So 2 pi times delta t over period, or delta t over t, whatever. Okay, so delta t in this case would just be um, the half point of each wave, or the, yeah, no, the half point of each wave. Okay, so the difference, obviously. So here, the half of the wave of the light string is 0.2, and the one for the heavy string is 0.3. So then you do the delta t would be the difference between those two, so 0.3 minus 0.2, which gives you 0.1. And then for the period, you're just going to use the period you originally have, which is 0.4. So 2 times pi times 0.1 over 0.4, and this gives you the phase difference. So 2 times pi times 0.1 over 0.4, and you get uh, so 1.57 or 1.6 pi. No, just 1.6. Sorry, just 1.6 if you substitute in pi. So the unit for this, right? So delta t is in seconds and periods in seconds. The unit cancels out, and we're left with 1.5 pi, or 1 over 2 pi. And the unit for pi is radians, so RAD, rad. So 1.6 rad, and yeah, that's the correct answer. Now, question 5. Define the capacitance of a parallel plate capacitor. The capacitance of a parallel plate capacitor is just the charge over voltage, or charge over potential difference, where charge is on one plate and the potential difference, and the potential is the potential difference across the plates. Okay? It's just a definition you're going to have to memorize, so you can find that definition um, in the thing I showed you. So now we're going to have to, I guess, apply a formula. They're always going to ask us of that. So two capacitors of capacitances C1 and C2 are connected in parallel to a power supply of EMF E1 as shown in figure 5.1. Show that the combined capacitance of the two capacitors is given by that formula. So we're going to have to derive that formula, basically. So um, the voltage across both capacitors is going to be the same because it's a parallel circuit. So this is going to be equal to the electric EMF, right? So V is equal to EMF. So we could say, in that case, we could also say that the charge is the same across all of them because C equals to Q over V. And then because, wait, yeah. So the charge in a the charge in a parallel circuit is the same. Therefore, we can say Q, so the Q total is just equal to Q of 1 plus the Q of 2. And then what do we know about the formula for capacitance? It's C equals Q over V. So we can rearrange it to be CV equals Q, right? So here, C total, and the voltage is the same, equals to C1, same voltage, plus C2 and the same voltage because the voltage is the same across the parallel circuit. So then you can cancel out V, so this, and this, and you're left with CT is equal to C1 plus C2. Next. So 5C part 1. Two capacitors of those capacitances are connected into a circuit of figure 5.2, as shown in 5.2, okay. Battery has EMF of 12 volts. Show that the combined capacitance of the two capacitors is 15 microfarads, sorry. So when you have capacitors in series, you do 1 over C1 plus 1 over C2, and you get 1 over CT, the total capacitance. So, um, let's do that. 1 over 22 plus 1 over 47. You get 15.98 or 14.98 or 15 microfarads. Okay, next. The two-way switch S is initially at position X, so the capacitors are fully charged. Now, we're going to have to calculate the total energy stored in these two capacitors. So, this is going to be, what do we have here? We have voltage, and we have capacitance of the two capacitors. So we can just say half CV squared. I believe that should work fine. So 0.5 times C, which is 15 microfarads, times the V squared. So 12 volts all squared. Please give me a correct answer. Yeah, 1.08 times 10 power negative 3. Here they wanted two significant figures, so 1.1 times 10 power negative 3. Part 3, I'll get back to it by the end of the paper because it takes so much time. Because it's like
It's complicated, okay? So how are you finding this so far? Is this helpful? I know I'm taking my sweet ass time, like we still have a lot of questions. Oh my goodness, we have a lot left. And yeah, but like how are you finding this so far? Is this helpful? Yes, okay, alhamdulillah. So state the two conditions that must be satisfied for a copper wire placed in a magnetic field to experience a magnetic force. There must be a current in the wire, and the wire must not be at an angle 0 to the magnetic field. That's it. Now, part B. A long air cord solenoid is connected to a power supply, so the solenoid creates a magnetic field. Figure 6.1 shows a cross section through the middle of the solenoid. Right, okay. So the direction of the magnetic field at point W is indicated by the arrow. Three other points are labeled X, Y, Z. So draw arrows in the direction of the magnetic field of each of the points X, Y, and Z. So at X, so let me just replicate this, right? So W is going to leave like this, right? Straight away. X, since it's not directly in the center, it's going to leave like this. Okay. And Y is over here. So we can just like imagine it to be like this. So like that. And then Z would be, so where Z is over here. Z would just be, so let's just like draw like imaginary line for now. So it goes like this, like this, like this, like this. Okay. So then it goes in this direction. You understand how I got that? Goes like this, rotates around, and then goes in this direction. Okay, hello. Now, 6. Compare the magnitude of the flux density. Okay, so at W and at X, they're nearly equal. Okay, and then the flux density at Y versus Z. Z has the weakest flux density because it's nowhere near the cross section of the solenoid. It's literally outside of it, so it's experiencing very, very little flux density compared to Y, right? So yeah, next. Two long parallel current carrying wires are placed near each other in vacuum. Explain why these wires exert a magnetic force on each other. You may draw a labeled diagram if you want. So the current in the wire creates a magnetic field around the wire, and each wire sits in the magnetic field created by the other wire. So they experience a force since the wire is perpendicular to the magnetic field. Let me just draw you the diagram so you can get a better understanding of it. So you have two wires, right? And they're current carrying. Okay, so two long wires. So let's just say the current is traveling in this direction, right? So now we're going to use the right hand grip rule. So you know the one where you take your right hand, you point in the direction of the current with your thumb up, and then you curl your fingers around. So in this here for this wire, you're going to have a magnetic field that's into the page, and then it leaves from this, and then it's going to be in the page here. So into the page and out of the page. Yeah. And then here you're going to have, so let's just make the magnetic field bigger because yeah. So here it's into the page, here it's out of the page, and here it's going to be into the page over here. So let's just draw magnetic field lines.
and then it's going to be out of the page here, and then we can see that these magnetic field lines exerted by each wire interact. So the magnetic field lines, a magnetic field of this wire it causes a force on this wire, and the magnetic field of this wire causes a force on this wire. Um, and since the wire is perpendicular to the magnetic field, it experiences a magnetic force. So here we can say current in the wire creates a magnetic field around the wire, where each wire sits in the magnetic field created by the other. And since the and for each wire, since they are perpendicular to the magnetic field made by the other wire, they experience a magnetic force. Next, alright. State Faraday's law of electromagnetic induction. Faraday's law of electromagnetic induction states that the EMF induced is equal to the rate of change of magnetic flux density, or magnetic flux linkage, rather. So, this is just a simple formula. I know EMF, that's not how you write an F. Oh my god. Induced equal to rate of change of magnetic flux linkage. Alright, next okay, so let's actually read the question. So,
I think when I solved this past paper on my own, this is where I stopped. So yeah, this is not fun. I hate this part. Because I hate anything like electromagnetic, you know?
it's not nice. No one likes it. Just give me a second. I'm gonna take like a 10-second break. Okay, so two coils are wound on an iron bar as shown in figure 7.1.
Coil 1 is connected to a potential difference that gives rise to a magnetic field in the iron bar, and figure 7.2 shows the variation with time t of the magnetic flux density uh, B on the iron bar. Oh goodness. Excuse me. So the voltmeter measures the EMF V2 that is induced across coil 2. So let's have a look at the question. On figure 7.3, sketch the variation of T with V2 between T equals 0 and T equals 0.4. So it's going to look something like this. Do I have the graph for this? I don't. Great. Hello. I don't have the solution for this, but you can you can find the solution on YouTube. If you look for it, I've found a video that explains this before, so it's okay. And by the way, I also I suggest if you don't know a question, look it up at YouTube. Okay, it's really helpful. Now, coil 2 in part B is replaced with a copper ring that rests loosely on top of coil 1. The supply to coil 1 is replaced with a cell and the switch that is initially open. The switch is now closed. As it is closed, the copper ring is observed to jump upwards. Explain why this happens.
So this is part C, I. So initially, what did we have? Initially, we didn't have any current in the wire, right? Here we have a current due to a battery. So a change in current, or changing current in coil causes a changing magnetic field. So no, actually we did have a current before. Why am I being so retarded? It's connected to a potential difference that gives rise to a magnetic field in the bar. Yeah, okay. But this time we change the current by connecting it to a battery and closing the switch. So changing current in the coil causes a change in the magnetic field. Now, an induced EMF in the ring causes a current in the ring, which in turn, the induced current in the ring is perpendicular to the magnetic field of the coil, so the ring goes upwards. Okay? So let me just summarize that real quick. Changing the current causes a no, changing current in the coil causes a changing magnetic field. Now, the induced EMF in the ring, in the current, Ya Allah, I can't fucking talk. Induced EMF in ring causes a current to exist in the ring, right? So the induced current in ring perpendicular to the coil's magnetic field causes the ring to move upwards. Or instead of that last point, you can say magnetic field due to the induced current in the ring interacts with the coil's magnetic field to cause an upward movement on the field, on the ring. Now, suggest to the reason what would be the effect of repeating the procedure in part CI with the terminals of the cell reversed. Uh, Nothing changes because the current also changes in the ring and in the coil. So here they reverse this cell, right? So the current in the ring and in the coil is reversed. Therefore, magnetic fields both reverse, so it still jumps off. It still jumps up. Sorry. Did you get this question? Thank God this is the end of this, because this is not fun. I hate anything to do with electromagnetism. So let me just see. Are you okay with this? When did you send that last? Yes. Okay, it's not. I hope you're okay with this though. Okay, I assume you're fine with this, so I'll just move on. State one piece of experimental evidence for the particulate nature of electromagnetic radiation. Okay, so you can just say photoelectric effect for part A, and then you can search up photoelectric effect if you don't know what it is. So photoelectric effect is just the emission of electrons when electromagnetic radiation hits a material. Okay. And then the wave nature of matter is due to electron diffraction. So here, one piece of experimental evidence. So the particulate nature of electromagnetic radiation is just going to be due to photoelectric effect. And then wave nature of matter is just going to be due to electron diffraction. Now, calculate the de Broglie wavelength of an alpha particle moving at the mentioned speed. So the Broglie wavelength formula is wavelength is equal to h over p, where h is Planck's constant. Okay, now Planck's constant.
Planck's, wait, no, Planck, it has, I think Planck has two constants, no? Wait, let me see. Yeah, no. So you're looking at this one. Yeah, yeah. So you're looking at the 6.63 times 10 power negative 34, right? Yeah. Okay. So 6.63 times 10 to the power of negative 34. Let's go back to the question. That was question 7 now. Question 8. Okay, we're actually getting somewhere. Let's go snap. Never mind. So, moving on to speed of 6.2 times 10 power 7. So 6.2 times 10 power 7. This is our speed, okay? And here we're given momentum, and we know momentum is equal to mv. So we already have v, we just need to find m. Okay. Now, the mass, this is an alpha particle. An alpha particle has a mass of 4u. Okay, so this is our mass. Now, what's u? U is 1.66 times 10 power negative 27. So 4 times that. So 4 times 1.66 times 10 power negative 27 gives us this value. Okay. Now, um,
This is our mass. Multiply that by our velocity. So 6.2 times 10 power 7. And you got our momentum. Now we have to do 6.63 times 10 power negative 34 divided by the momentum. And we got a value of 1.6 times 10 power negative 15. They got a value of 1.6 times 10 power negative 15. So, yeah, this is correct. Next question. Oh, wait, what? Am I saying this correctly?
it says there's two people watching the live, so I guess both of you are here. That's nice. Okay. Yeah. Okay. Now the speed v of the alpha particle is gradually reduced to 0. Sketch the variation. So it's just going to be like a curve. So like let me draw it for you. So you have wavelength here and v here, and then 6.2. So it's just going to be like this, right? And you're going to have an asymptote, and you're going to have it be asymptotic to both the y and the x-axis. So, um, suggest an explanation for why people or humans are not observed to diffract when they walk through the doorway. The de Broglie wavelength is negligible compared to the width of a doorway. You just have to know the rules of diffraction to be able to answer this question. So, yeah, next question. Question 9. State Hubble's law. So this is an astronomy question or astrophysics question. So the speed is directly proportional to the difference where speed of recession from the galaxy in terms of the observer and the distance is the distance of the galaxy away from the observer, right? So I just read, this is just the definition I read from the marking scheme. I'm sure you can also find definitions in the website I was talking about earlier. So astronomy and cosmology, right? So as you can see, they have no questions for this. It's that new. You really can't find any questions about this. So inshallah this year it's not hard or anything. But definitions, flashcard, these, yeah, definitions. So Hubble's law. Here, the speed of the galaxy moving away from ours is proportional. So the speed of a galaxy moving away from our galaxy, is proportional to the distance away from us. So it's the distance of the galaxy away from us The constant of proportionality is Hubble's constant. So explain how cosmologists use observations of emission spectra from stars in distant galaxies to determine that the universe is expanding. The wavelengths are greater than their known values, so redshift shows stars in distant galaxies moving away from the Earth. Again, you're just going to have to read about this in the book to actually know how to answer this. And I don't really know how to explain it the best, so I don't want to overcomplicate it for you guys now. Explain how Hubble's law and the idea of expanding universe lead to the Big Bang theory of the origin of the universe. The universe is moving away from each other, so every part of the universe is moving away from each other, and the objects that are farther away from us are moving away faster. And before before the Big Bang, matter must have been in a very, very dense point in the past. That's 3 marks. That's 3 things you can say to get those 3 marks. So we're on our last question. We actually finished the rest of this paper really quickly. Actually, no, I still have wait, don't I still have like a whole last question or some shit? No, no, no. Yeah, I just have um so I have the RC and I have question 2 last part. Okay. So state what is meant by radioactive decay. Okay. Radioactive decay is the spontaneous emission of radiation from an unstable nucleus. Okay. That's 2 marks. That's 2 things you can say for 2 marks. Now, a radioactive sample consists of an isotope X of half-life T that decays to form a stable product. Only X and the stable product are present in the sample. Okay. At time 0, the sample has an activity, at t equals 0, the sample has an activity of A and contains N0 number of nuclei X. On figure 10.1, sketch the variation with T of the number N of the nuclei X in the sample. Your line should extend from T equals 0 to T is equal to 3T. Okay, just give me a second, guys. So T is the half-life. Right, so I'm gonna need to do this. Right, okay, so first of all, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 1, 2, 3, 4, 5. So this is going to be 0.125. Let me make the line a bit skinnier. Yeah, okay. Okay, so a radioactive sample. Okay, so half-life T, and at time equals 0, it has an activity of A and contains N0 number of nuclei. So let's just plot our points. So initially it had the full number of nuclei because at T0 it still didn't experience a half-life. Then at the first half-life, it's reduced to obviously half the number of nuclei. So our first half-life is here. So right, so this is going to be our point over here. And then wait. I messed up. Guys, half of 1 is 0.5, not 0.25. Okay, please don't be dumb like me. So 0.5 and then yeah, so right about here.
And then at the second half-life, 0.5 becomes 0.25, right? So yeah, okay. So this, and then we're going to plot the one for 3t. So 0.25 because 0.1, sorry, 0.125 because it is half of 0.25. So just stretch it out until here. And then we're going to draw the curve. So it's going to be a decreasing gradient curve like this. Yeah. Okay. Where did paint go? Okay, yeah. Next. That was 3 marks? God damn, okay, that's 3 free marks. On figure 10.2, sketch the variation with n of the activity A and of the sample for values of n between 0 and n equals n0. Huh? Sketch the variation with n of A of the sample of values of n between n0 and n equals to the initial value. So I believe it's just going to be, yeah. Right. Yeah, I believe it's going to be a straight line through the origin in this case because the activity and the number of molecules are proportional to each other. So yeah. But here they want the variation. So let me just double check this. I think I know what it's going to look like. So I think it's going to look like this, but I just want to double check it either way. So no, wait, here. No, that's it. It's just a straight line. Okay. Yeah, okay. I understood the marking scheme wrong, but yeah, it's just a straight line passing through the origin, guys. That obviously has to go to this endpoint over there. Now, question after it. State the name of the quantity represented by the gradient of your line in figure 10.1. This is decay, wait, 10.1. So the, what, the gradient? Huh? Quantity represented by the gradient. Okay, so when you divide n by t, you're getting the activity, right? And when you divide a by n, you're getting the decay constant. So for figure 10.1, the gradient is going to be activity, and for figure 10.2, the gradient is going to be the decay constant. Now, last question. For the sample in B, calculate the fraction n over n0 at time 1.7t. So there's a formula, you're supposed to know it. Alright, so n equals to n0 e to the power of um, negative ln2 times 1.7 t over t. Let me just double check it. Actually, the guy had the formula written down in the video. If we just go back to it. Oh, where did he get ln2 from? Uh-huh. Okay, so n0 e to the power of negative wavelength times t. Okay, and this is the same thing for A. For activity equals activity initial e to the power of negative wavelength times t, as you can see in the video over here. So calculate the fraction. So it's n over n0, so we're just going to move n to the other side. So I'm just going to bye-bye this formula for now. Hello, can you please? Okay. Right. Okay, so the fraction, so we're going to move this to the other side. So n over n0 equals to e negative wavelength t. And now you're just going to substitute. So do we have the wavelength in this case? Did we calculate it? No. Hmm. Wait, give me a second for this one, guys. Because I'm gonna look through my notes because I did this. I did this one specific question, I remember. Yeah, so the wavelength. There was, I swear there was a formula I put up earlier for the wavelength. No? Activity equals wavelength something. Oh my god, wait. They probably give it to us here. And they don't. Yeah, they don't. God, what was the formula? I literally had it. I remember. Right here, we can get it from this now. Frequency represented by a line. So activity is equal to the n over t. No? And then decay constant, which is our the not the wavelength, like this icon here, whatever, lambda, is ln2 over half-life, or in this case, activity over n. But yeah, oh, I just remembered it. Perfect. Okay, so yeah, the half-life is equal to ln2 over lambda, right? And we have the half-life. They are presented to us as big T. In this case here, you can see they tell us the half-life is big T. Therefore, when we substitute n over n0 equals to e to the power of, so what's lambda? Lambda is ln 2, so ln 2 over t times 1.70t, so 1.70 t. So this and this cancel. So we're left with ln 2 times 1.70. Of course, all that exponential. So e to the power of ln 2. Here they take ln 2 to 3 significant figures only. So 0.693. That's a rule you're gonna have to know. So e is negative 0.693 times 1.7. And we get the ratio of n to n0 as 0.307, or in the mark scheme, it is 0.31. Okay. Yeah, guys, I'm gonna end it for now. I'm gonna take like a break, and then I'm gonna continue later on, like tonight. I'm gonna solve past paper 21 of the year 2021. The questions that I didn't do, I will send them on the group, so don't worry about that. I'm just gonna wait for your feedback. How did you guys find this? Like, was it helpful? Do you have any complaints, or, you know, just let me know. How was it? That's great. Okay, I'm glad I can help you. Did you understand anything? I assume you did. I hope you did. Now, the 2021 past paper is not going to be the syllabus. It's not going to be the full syllabus that we're going to have an exam. I only need to practice. Yeah, no, trust me, I need to practice too. But it's because I'm a bit rusty. But it's okay. You're gonna get through it, and inshallah, you get that A star. So yeah, I'm gonna turn off the stream. I'm gonna do one again tonight. So yeah, I'm glad I can help you, Reem. And if your friend Hamza is watching, Masai, I don't think she is. I'm not sure. Wallah. Oh, three watching now. What? Three? Okay, so my laptop and then you and okay. Hello. So yeah, I'm gonna explain the rest tonight, and the questions I didn't do tonight. You're welcome. I'm glad I can help you. Okay. Yalla, have a good rest of your day, guys. I'm gonna see you later, inshallah. Yalla, bye bye. Take care.